All right, so this guy, let's see, 4, 3, what did you say again, 15? Yeah. Negative? Yeah. All right, and this one says it's got several parts to it. Oh my God, I got so many colors. Don't even work. So part A says find the intervals where it's increasing, decreasing. So what do you need to do that? Find the derivative, because that's what controls the slope, which tells you when it's increasing, decreasing. So what is the... I like it. So sometimes people don't write that 2 like it came down, but what rule am I actually using from here to here? Chain rule, I love it. So it's a nice little shortcut, e to the ax. Derivative will be a e to the ax. But it's not coming down, it's just chain rule. It just kind of looks like it came down, I guess. So it's a nice little shortcut. Cool. Now, what do I do with this? Find out where it's 0 so I can see what side of it's negative, positive. I like it. 0 is the dividing point between good and evil. Or negative, positive.
But before that, we can fraction it, right? Fraction.
Let's see. If I set this equal to 0,
E to the negative
divide by 3. How about this real quick? Is there anywhere where it's undefined?
No.
No, because e to no power can become 0. In fact, no number to a power can become 0. And the limit would be 0, but it would never get there. So I could multiply both sides by
E to the negative x.
By e to the x. Let me stop there. What would you do if I had this? What would you do if I had 2x minus 1 over x equals 0? You would actually, but then what you would do, you would multiply by x. So this is 1 over e to the x, so I can multiply by e to the x. It's one way to go. So if I do that, what do I get here?
So you need 3x minus
You can do it.
yeah. 1.
Yeah. X minus x is 0, e to the 0 is 1. So that's a little bit easier. So then you can add 1, divide by 2, and Jonathan, your question was, you took an ln some point, yeah. Is that cool so far? There's several different ways to go from there to there, but you've got to end up here, and then you can take ln. Come on, 1. And then divide by 3. So that is what? What is that?
That's a critical number.
Critical number, I like it. So it's where, what could happen? Min or max, I love it. So it could be a turning point. That's another way to talk about it, right? What is this approximately?
Negative 0.23.
0.23? Okay.
I did 2
I like it. It's cool to me. All right, so to answer part A, it's asking me where it increases and decreases. I just have to see where's the slope negative, where's it positive. So I do go all the way through the sign diagram, right? So now I've got my natural log of 1/2 over 3, which is about this. When you do this, this guy is nice. Polynomials, exponentials, their domain is everything, but this is why I asked the question, what's the domain? And you should expect that question, because if the domain was negative infinity up to 1, then when you make this, you wouldn't think about anything past 1. It's why domain is important. It's controlling what you have to worry about when you're investigating the derivatives. Okay. So, what can I plug in? So this is negative 0.23. That's what that really is. So what can I plug in on this side? 0. And when I plug a 0 in,
Positive.
I get, what do I get?
1.
2 minus
1
is 1. It's great, so it's positive. And when I plug a negative 1 in, or it doesn't really matter, but now you get like 2 e to the negative 2 minus e to the negative 1. whatever the hell that is. It's going to be negative, yeah. You can plug it in the calculator, right?
Wouldn't it be E?
I think it'd be negative. Let's see, 2 over e squared minus e over e squared. 2 is smaller than e, so it'd be negative.
Wouldn't it be E to the 1?
Oh, e to the 1.
That's what I was saying.
My bad. So negative 1, that's what we're plugging in. So that should be 1, yeah. So now it's even easier. 2e negative 2 minus e, that's still definitely negative. 2 divided by e squared minus big ol' e, that's going to be negative. So it should be negative back there. I like it. Alright. So that is a normal part of the process when I'm going to graph something. Here, this is broken down for me, like I'm going to break it down for you. What intervals is it decreasing on?
Negative infinity to 0.
Negative infinity to this mess, right? There's a better way to write that, but oh well. And then increasing, of course, in the other part. I like it. So that means that that's the location of a...
That's a max.
Yeah.
A min.
It's going down to it and up from it, so that must be a min. Is that what part B is?
Yeah.
Where'd it go? 15. Part B, find the local max and min value. So it's only got a min, it seems. It doesn't have a max. So then you just plug this in. And you should plug this in, really. Because that's the exact critical number. I know some of you guys look at me, but you're in calculus. You shouldn't be looking at me like that, right? If you're in Math 90, you could look at me like that. You're in calculus. So what is f of natural log of 1/2 over 3? Well, it's going to be e to the 2 natural log of 1/2 over 3 plus e to the negative natural log of 1/2 over 3. You should be able to plug all that in your calculator. What you can also do, let me show this to you, because this is very useful. I don't know if you guys have all seen this. Oh crap, I just changed my password.
Oops.
No, I haven't. Well, scheiße. Okay, that looks like it worked. Okay. I hate that. Your password has expired. Oh, shit.
You used to change the last number.
Yeah, I was doing that for a while.
Yeah.
But now I had to change it all the way. I don't want to go to 10 because I'm going, oh, shit.
I don't know what it's already.
Yeah. I just made it 1, 2, 3, 4, 5 minutes. Make it easier. Alright, so if you do natural log of 1/2 divided by 3. And I don't know, have you ever used this button here? See that button right there? Stow. Mm-hmm. Like stow it away. Store it in X. So now that value is in X. So now I can just do this exactly the way it looks. It kicks ass. I can say, so I want to know what's e to the 2x, because what's x have? X has the value of that crap in there. You guys kind of with me? Mm-hmm. Plus e to the negative. No, Jeff, that's minus. Here's negative x. So you can close that door right there. Thank you. It'll only help out a little bit.
So how do you store x?
Oh, you could either. So if I put in there natural log of 1/2 divided by 3 and I hit enter. So I see what it is. But now you can immediately hit the store button. It'll say store. Oh, you mean the last thing that was on the screen? Store it in X. Now, if you wanted to store more things, you can hit the alpha button and then pick any of those green letters.
That one works for TI-84 plus?
Yes.
What do we have to 83?
Oh, no, it works for 83 also. Yeah, yes.
I'm trying to find this old value.
What is it? So now X has that value in it. Is that cool? If you want to. Because what's the most important thing? If you take any science classes, anybody know, did I ever ask you about, like, who knows about significant figures? Sig figs? Alright, so it's related to that. The most important thing about it is you don't round to the end. If you round too early, everything starts to error propagate. You're off and off and off more. So this kind of thing helps you to not round at all. That's what you really are shooting for. And then at the end, you can round it to graph. right?
1.88983.
Yeah, exactly. Cool. I like it. So that would be the min. It would be this, comma, 1.88 below. And part C, intervals on concavity. And of course, to look at the concavity, I just look at the second derivative. And can somebody tell me what concavity is? Besides,
It's how the slope is changing.
I like it, how the slope is changing. So if the slope was positive, but it was becoming less positive, like I'd say, the unemployment is rising, but not as quickly. What kind of concavity would that be? What do you think? So it's rising, but it's not rising as quickly. Would mean it looks like what? Who can do that? Yeah, exactly.
It's a downward.
So it's still going up, but it's not going up as quickly. And we hear that kind of thing in the news all the time. And like I said before, they don't even realize they're talking calculus, right? So this is why the slope is obviously getting less. So the change in the slope is negative because it's getting less. That's why it makes sense that a second derivative less than 0 means concave down. It doesn't mean it has to look like this. This is concave down. Does it look like this? No, it's just a piece of that. It just means it's going in the direction it's going in this manner. You guys kind of with me? So if it was going from here to here, and I was saying it was increasing, the slope was increasing, then it's going like that in that manner. It doesn't actually have to make a whole. My goodness, I might as well sing some blues. It doesn't have to make a whole parabola, a little piece. It just means this is the curvature of it. That's what's important. Do you want to do that? I don't know. I mean, all I have to do now is take this second derivative. What would that be?
4 e to the t is plus e to negative.
I'll look, plus e to the negative x. Then you set that equal to 0. We do the same thing we did before. I end up at 4 e to the 3x plus 1 equals 0. If I do the same thing I did before. Now what happens here though? Is this possible?
No.
Why? Because e to the 3x can't even become 0. So how the hell is it supposed to get down to negative?
No solution.
You guys see? Yeah. So what does that mean?
It's always going to be a deposit.
Yeah, there's no way of.
No critical numbers. So your picture looks at it as one giant region. So plug something in, and that's what the concavity is everywhere. There's nowhere the concavity could change. That's what that would mean. I like it. So if I plug whatever you want to, let's 0. I really want you to understand. There's nowhere it could. Yes, Denny?
I just wonder, where did the 3x come from before?
Oh, so I did the same thing I did over here. Multiply both sides by e to the x. Got here, no good. So don't freak out if this happens to you. It just means there's nowhere it could change. It's just always the same. And what's the simplest function that acts like that? That always has the same concavity.
Or L to the x.
That's a nice, I like it, e to the x, L and x, but the simplest one is one that's already freaking parabolic, like a parabola, x squared. It always has concavity up, right? It doesn't change anywhere. There is one place where it might change, but no. So here it doesn't even have a place where it rests. This is always concave something. And when you plug a 0 in, you get 4 plus 1, you get positive. So it's always concave up.
What if we didn't know that and we just went and solved for x?
You run into a problem, because what would you have to do if you did e to the 3x equals negative 1/4? You try to take an ln. Can you take an ln of negative? No. So even if you didn't see it, the math will still say, hey, dude, no. Right there, it's like, oh shit, I can't do that. I like it. All right, and then here, there's no inflection points to find because there's no changes in anything. So here you say, what's the interval that is concave up on? Concave up on what interval? Negative infinity to infinity. I like, because the domain is all real numbers, so it's concave up on its entire domain. There's nowhere where it could change. Because there's no critical numbers. It can't change anywhere. Does that make sense to me? That's what critical numbers are. They are the places where things could change. Bless you. If there are none of them, things can't change. Whatever they are anywhere, it's always that, whatever that thing is you're looking at. So there are functions that only increase or decrease. There's functions that only, e to the x, I love e to the x, is always concave up. It's a beautiful example of that. I love it. Okay. Because what's the derivative of e to the x? What's the second derivative? Is that ever equal to 0? No. So there's no critical numbers of anything. It's always concave up and it's always increasing. So it's got no critical numbers anywhere. Okay, that was interesting. Yes, ma'am.
45 on the 4.1.
4-1. Oh, cool. All right. Well, we did this. I don't know if we actually graphed it. Did you try to graph it? I mean, hopefully you noticed whenever they have that red symbol, they're not asking you to do it by hand. That would be basically impossible. You have to graph it. And the thing to realize with that problem is it is the derivative they've given you. So the critical numbers occur where? And I wasn't as technical as I should have been. I looked to see where the derivative is 0. Where else do critical numbers happen?
Undefined.
Undefined, but obviously this is a nice function. This is not undefined anywhere. Is that cool? That was my whole point about this can't be 0 anyway, so it can't be 1 over 0. It can't be undefined. So the function they give you there is basically trig with a dampening factor, right? So you graph it and you just see it's a derivative itself. So you just have to see, if I graph f prime, where would the critical numbers be? So here's f prime. Where are the critical numbers? Oh, I like this question.
So, okay, for f prime, it's where zeros are at. Where the
Where do the critical numbers happen for the first derivative? Where the first derivative is 0 or undefined. Well, where is it 0? There, there, there. So you plot the function they give you. It is already the derivative. You actually don't have to do any calculus to it. You just have to apply calculus idea. Where is this function equal to 0? And at some point it stops being equal to 0. So the number of times it crosses the x-axis is where that's the place where it's 0. That's the number of critical numbers it's going to have. Does that make sense? All right, so critical numbers happen where derivatives are equal to 0 or undefined. Cool? So if I graph a derivative, where are the critical numbers for that derivative, where it's equal to 0. So you just have to graph the function they give you and see how many times does it cross the x-axis. Those are each a critical number. Because those are each somewhere that f prime is 0. That's how you find critical numbers. I really want that to make sense.
You said critical numbers are where it's changing though? So
Yes.
not on the x-axis.
But be careful. I really want this. This is a picture of f prime. So if I looked at f, critical numbers would happen where if this was f, that would be a critical number. That would be a critical number, right? Because that's a turning point. And there might even be another critical number that just didn't happen to turn. So there's at least as many critical numbers as there are turning points. Let me say that again. Does every critical number end up being a turning point or a inflection point? No. Is that cool? Because that's why we have to test them. They're not guarantees. But if I see a picture already, if I see f, where are there definitely critical numbers for this? At the max and the min. But this was a picture of f prime. So where do the critical numbers for f happen? Where it is 0. And it's not undefined anywhere for that function, so nothing comes from that. I like it. So that's a weird question because they gave you the derivative. So part of your brain says, I have to take a derivative. No, they've done it for you. Yeah. Thank God, because that's a disgusting function. Poor little function. Disgusting function. What's your function?
Yeah, well, there you go.
What were absolute extreme values?
Oh, good. So I didn't put any of those on the quiz because I'm hoping those are, and you're booing for the right reason because those should be relatively easy. They're a lot easier than finding local maxes and mins because they don't have to do any tests. I just have to plug them in and see who wins. It's almost too nice to believe. So students try to make more out of it than that. So if I have a function that's domain has been cut somewhere, where are the only places that an absolute max or min can happen? So say it's cut between those two. Well, this one's kind of boring. This one's boring. Why? Where do the absolute maxes and mins happen?
At the endpoints.
At the endpoints. Now, if I cut this one there, where's the absolute max happen?
Right there.
And this would be a what of f?
That's a local max.
True, but in a critical number, I like it. So they could occur at the endpoints just by the fact that I cut it off. So it could go lower, but I cut it right there. Too bad. So it could happen at the endpoints. Endpoints got lucky just because of the way the domain was cut, or it could happen where that always happens at the critical numbers. So that's why this is really almost too nice to believe. And you guys, whenever I say that, you're like, whatever, man, tell the truth. But let me see. Let me give an example from the book. They talk about absolute maxes and mins in this 4.1 also, right? Here it is. Okay. So like this. Number 50. You can pick the book up and take it with you. That would be too easy. I guess, I don't know. Alright, so I got my endpoint. So I already know I want to check out f of -3, f of 5. In between those two, I want to check out all the critical numbers, because it either happens at the endpoints, just the way it was cut, the way the domain was cut, or in the middle, wherever the local maxes and mins happen. They could be an absolute max or a min. Does that make sense? If it makes sense, you go, oh, thank God, give me a lot of these, Jeff.
A lot of them.
A lot of them, just a lot of them. So I'm going to give you like one. What's the derivative?
3x squared minus
12 x.
Okay, cool.
Set it equal to 0.
And what are the critical numbers?
X
minus 4.
0 and 4.
Are they both in the interval?
Yes.
Yes, good. So you do check, make sure that you don't plug something in that's not even in the interval of things you care about. They're both there, so I'm going to check both f of 0 and f of 4 out. Plug them all in. Of course, you're plugging them into the f. I'll do f of 0. Yay, Jeff. Yay. And the rest of you got a freaking calculator, you can plug it in there. And you just step back and see who's the biggest. That's the absolute max. Who's the smallest? That's the absolute min. That's almost too easy to believe. Please let that be easy. Please. If you can take a derivative and you can factor, you're okay. Yes?
Can you do 4.2 on number 7?
Is everybody cool with that one? Do you need me to finish that one out?
Yeah.
Oh, you
So
gotta,
that's the same as the absolute extreme value? Like,
yes.
Okay.
So,
it's like
a quick way to say maxes and mins is just to say extrema.
okay.
Extrema is both max and min.
Okay. All right.
Right?
All right. Thanks.
Cool. I like that. Because you get the highest point on Earth, but you also have the lowest point on Earth, one of those trenches or whatever down there in the ocean, right? Mm-hmm. So that's the extreme positions of Earth, right? That's the extrema of Earth. Sounds like a weird book. The extrema of Earth. So which one? I'm sorry. Who's?
4.2 on number 7.
All right. Let's see. I like it. This one is a visual problem. No, the neck of my poor little dude is dying. It's amazing how things have to be turned on to work. Jeez. How did they come up with the logo? What was that meeting? I like Rubik's Cubes. Alright. So this one here, right? So this one?
Yeah.
Alright, that's better, right? Alright, so from 0 to 8. So what you're going to do is you're going to get over the any aversion you have to drawing in your book. I don't have a pencil with me, but this is my book, so what the hell? So So from 0, and this is 8, where they're not killing me. 2, 3, 4, 5, 6, 7, 8. Okay. So from 0 to 8, now half of the mean value theorem